Good morning, students. In this video, I would like to discuss with you about synchronous counters. We have already studied about asynchronous counters. Counters are a group of flip-flops that can be connected to perform counting operations. So, if a counter consists of n flip-flops, then it may count pulses up to 2 raised to n. That means if we have 3 flip-flops, then we can count 8 numbers. That means from 0, 0, 0 to 1, 1, 1 in binary. Counters are classified into asynchronous or ripple counters and synchronous counters. We already discussed asynchronous counter. This is the logic diagram of asynchronous counter in which we are using 3 flip-flops and the clock is connected to the first flip-flop and the clocks to 2 other flip-flops are output of the previous flip-flop as shown in the figure. So these type of flip-flops do not receive the same clock signal, then it is called asynchronous counter. Coming to synchronous counter, when counters is clocked such that each flip-flop in the counter is triggered at the same time, the counter is called synchronous counter. Synchronous counters are so called because the clock input of all the individual flip-flops within the counter are all clocked together at the same time by same clock signal. Therefore, it is called synchronous counter. This is a single clock pulse in which it is a positive clock pulse because it's activated in the rising edge. See this arrow, rising edge. The second one is negative clock pulse in which it is activated at the falling edge. See on the negative half cycle. This is the logic diagram of synchronous counter in which we are using 3 flip-flops. Clock is connected to all flip-flops simultaneously. So clock is connected to all flip-flop from a single source. Then the input J and K of first flip-flop is connected to logic high or it's always high. And the output of first flip-flop FFA is connected to the inputs of second flip-flop, particularly J and K. And it is also fed to the input of a AND gate. The output of second flip-flop FFB is connected to the input of the same AND gate, and the output of this AND gate is connected as the input to third flip-flop, and we are taking output from QA, QB and QZ. Coming to the working of synchronous flip-flop, QA changes on each clock pulse as we progress from its original state to its final state and then back to its original state. To produce this operation, flip-flop A is connected in the toggle mode by connecting J and K inputs to high. So, in each clock pulse, the output QA gets toggled. That means if output is 0, after the first clock pulse, it changes to 1. After the second clock pulse, it changes to 0. So, in each clock pulse, it's toggle its state. Now, the flip-flop B toggles when QA is 1. When QA is 0, flip-flop B is in the no change mode. The input of B is the output of flip-flop A. So, whenever this input QA or the output of FFA is high, the second flip-flop FFE get toggled. So, whenever QA is equal to 1, it's change its state. If QA is equal to 0, it retain its state. So, this second flip-flop will work depend on the output of first flip-flop FFA. The flip-flop C has to change its state only when QB and QA both are logically 1. This state is detected by AND gate makes J and K input of flip-flop C high. So the third flip-flop will get activated when the output of this AND gate goes to high state, because the inputs J and K of this AND gate, because the input J and K of this flip-flop Z is connected to the output of AND gate. To get high at the output of this AND gate, QA and QB should be high. So, whenever QA is equal to QB is equal to 1, we get this flip-flop, that is FFC, get activated and the output will toggle. All these flip-flop will toggle its state when it gets activated. So, initially, the outputs are 0, 0, 0, and we are always giving this input high. And when I am giving the first clock pulse, it gets changes to 1. Remember, in synchronous counter, we are giving clock pulse simultaneously. So, it will depend on the previous state. So, this flip-flop will check the input of J and K in the previous state. Now, when we are giving the first clock pulse, input is 0, therefore no change. Here also input is 0, no change. Before first clock pulse, this input is high, so the first flip-flop get activated and changes to 1. So I am giving a clock pulse, suddenly it changes to 1. Now, just before the second clock pulse, this input is high, therefore it will change to 0 after second clock pulse. Here, the input state is 1, therefore it will change to 1 after the second clock pulse. But here the state is 0, therefore no change. So, therefore, when I am giving the second clock pulse, this B output changes to 1 and A output changes to 0, and there is no change for Z output because the input was 0. Now, just before the third clock pulse, the input here is high, therefore it will change to 1 after third clock pulse. Here, input is 0. From here it went to here, therefore 0, therefore no change here. Here also input is 0 because this input goes to high state only when both inputs goes to high state. That means QA and QB goes to high state. Therefore, after the third clock pulse, A changes to 1, there will be no changes for B and Z. Now, just before the fourth clock pulse, this output A is high, therefore it will active this flip-flop, therefore it changes to 0. But when we are seeing the third flip-flop, the AND gate will go to high state because the inputs, this QA and QB is 1. Therefore, the output of this AND gate will be 1, changes to 1. So, after the fourth clock pulse, this changes to 0 because here the input is 1. This changes to 0 because here the input is 1. And this also changes to 1 because the input is 1. Therefore, when I am giving the fourth clock pulse, the output is 1, 0, 0. Remember, the most significant bit is C and the least significant bit is A, as same as that of asynchronous counter. Therefore, the digits are 1, 0, 0 equivalent to 4 in decimal. And I am giving the next clock pulse. Here 1, it changes to 1. Here 0, no change. Here also 0, no change. So when I am giving the next clock pulse, the output is 1, 0, 1, 1, 0, 1. When I am giving the sixth clock pulse, it changes to 0. Here 1, therefore changes to 1. Here 0, no change. Therefore, after sixth clock pulse, output is 1, 1, 0. And when I am giving the last and seventh clock pulse, this flip-flop changes to 1 in the output. Here 0, no change. Input for the third flip-flop is 0, no change. Therefore, the final output is 1, 1, 1. So this is the working of synchronous counter. This is the truth table of synchronous counter, in which when we are giving the first clock pulse, the output will be 0, 0, 1. For the second clock pulse, output is 0, 1, 0. For the next, 0, 1, 1, and so on. For the last clock pulse, that is the seventh clock pulse, the output is 1, 1, 1. So we can count from 0 to 7 in decimal. This is the timing diagram of synchronous counter, in which we have three outputs, QA, QB, QZ, denoted by A, B, C respectively. So when we consider the clock pulses, for the first clock pulse, QA goes to high state. We can find it from the truth table. See, this is the truth table, in which A output for the first clock pulse, high for the second, low for the third, for the fourth clock pulse, low or 0. So for the first clock pulse, it goes to high, continue it until the second clock pulse. For the second clock pulse, it goes to 0 state. For the third clock pulse, it goes to high state, and so on. When we are considering the second digit B, from this truth table, we can see that it will goes to high on the second and third clock pulse and on sixth and seventh clock pulse. So the B output will goes to high on the second clock pulse and it continues there until the fourth clock pulse. And in fourth clock pulse, it goes to low. Then it again goes to high state at the sixth clock pulse and continue there. When we consider next digit and most significant digit Z, the output will goes to high from the fourth clock pulse. So we can see it here. When we are applying the fourth clock pulse, it goes to high and it continues there until the seventh clock pulse. The major differences between the asynchronous counter and synchronous counters are, in this asynchronous counter, the output of first flip-flop drives the clock for the next flip-flop. Whereas in synchronous counter, all the flip-flops are clocked simultaneously. Whereas asynchronous counter, all the flip-flops are not clocked simultaneously. Logic circuit is very simple, even for more number of states. For synchronous counter, design involves complex logic circuits as the number of states increases. We know it because we are using a AND gate for 3-bit synchronous counter. And the main drawback of asynchronous counter is that the clock is propagated through number of flip-flops before it reaches last flip-flop. So, when we consider synchronous counter, the clock is simultaneous, therefore no problem of propagation delay. That is the advantage of synchronous counter. That is all about synchronous counter. Thank you.